will be mentioning again, I hope, if I remember, is that after this week, a week today, in fact, you're going to get your midterm. And your midterm is going to start at 7 a.m. and it's going to finish at 9. If that doesn't work for you, then it can start at 8 and it will finish at 10. Now, the midterm will be quite different from your usual online homework because you will be here. It's worth a lot of points. It's going to be a big influence on what your grade is. And one of the things that you need, or else I can't have you take the test, because for security reasons, everyone has to be treated the same and has to be able to check that there are no cheating going on, that you need to be online with a camera. I got to be able to see. See, right now I can see Autumn's on her own some. She doesn't have a big sister. She might, I don't know, but she doesn't have her big sister helping her right now. So I can tell that, right? So you need to have that done. So if you have not got a camera, you need to get one. You can borrow one, borrow someone's laptop, whatever it is that's got a camera on it, but you need one. So I don't want to find out on Monday, oops, I didn't know I needed a camera, because I don't think that's going to be a valid excuse since I've given you a week. Well, actually, I've mentioned it week 1, so it's not like you didn't know it was coming. So it's important that you get that sorted out. If you just want to test your camera out, you can drop into officers. We're at 10 a.m. We can make sure that all the hiccups and all that stuff is sorted out. That's a biggie. So if you just don't do your midterm, then you're failing the class because the amount of points you lose is so much that you couldn't possibly recover. So we don't want that. Second thing you're going to have to do is you're going to have to do your working. It's going to be on paper for the most part. Actually, it's going to be in 2 parts. Half the questions are going to be on paper and you'll write the answers. And the other half of the questions, you know, the ones that use salt, I'll have a dummy salt set up with the questions that need it, and you would do those ones, and that will cover that. So it's mostly on paper, but as you know, there are a couple of questions where you just have to use salt button, and that will be there. So once you've written all your work, you then have to use a program called Microsoft Lens, and you will upload it into Canvas. I will have a little practice Canvas module where you can just practice uploading stuff and seeing how you do it. Now on our Canvas shell, I've got all the instructions and a little video on how to use it. Now you don't need to use Microsoft Lens. Some of you from your English or other courses have used a different piece of software. That's fine, as long as you upload it into Canvas, that's good. So if you have scanners, that works as well. But Microsoft Lens will probably be the most likely version that you'll use. And that's, it's important, first as I get to see you working, because I can give you partial credit on that. Now, a lot of the questions that involve, here's a story, pick A, B, C, D, I'll be putting that half of the test in WebAssign. So, I mean, you're either right or wrong, so I don't need to see working for those. But the ones that are in a PDF that you'll get, those ones you should. So think of it as like the test is in 2 parts. One part is in Canvas, you show me all your work in, take a picture, upload it. And the other half, the stuff that's got salt or the multiple choice stuff, just pick a button and that one will do that. So it's a little bit of A, a little bit of B, but you will get a lot more points because I can see you're working. Right, any questions before we get started with today's topic?
Does that mean we'll need a printer?
No, you can just use Microsoft Lens. Essentially what you do is you take a picture of your working on your mobile phone, and this program that I talked about, Microsoft Lens, turns it into a PDF, and that's what you send to me.
But we'll need to be able to print out the midterm, right?
No, it'll be on a PDF that you can see on Canvas. So you'll be able to see the questions on your screen and you just write your answers on the paper.
Okay.
That makes sense, right? So I'll make up a question. I might say to you, probably will, not this specific question. What's the probability that you get a king or an ace? Right, that'll be on PDF, right? And so you'll write down you're working and you got your answer and it's 3/4, whatever. That's what I would see a copy of from your camera. And then you'll get other questions where use salt to find the probability, you know, that someone is over 50 years old. You know, you go into the salt button and you adjust the little windows and the answer's 2.4. Those ones will be in salt, will be in, I should say, WebAssign. I don't need to say working for them. They're all done by technology. And questions like, here is a story, which one of these 4 is the type of sample it is? You know, you pick box 1, 2, 3, or 4. That will be in WebAssign. That's the easiest way to do it because they're just right or wrong. So hopefully it's not too complicated.
Thanks.
The final is going to be very similar to that. So once you've seen the midterm, you'll know what the final is going to look like. Okay. Any other questions? Okay. We are going to be looking at the calculating probabilities, but we're moving up the food chain. Up to this point in time, we've really only done one event and found its probability. Even if that event is a little bit complicated, it was just one thing. It's like you take one card from a deck of cards, and what's the probability it's a king or an ace? Or what's the probability that it's an ace given that it was a red card? Or you used a contingency table, right? One of those 2x2 or whatever tables, and you got a single probability from that, which was something along the lines of, what's the probability? Okay, I've lost my darn screen already. There we go. So what's the probability? What's my thought process? Yeah, you get a contingency table. What's the probability that you voted Republican given you our mail? But it was one person out of a sample that was being chosen in each of these questions. Excuse me, this damn thing's annoying me. There we go. So what we're going to move on to today is how to evaluate probabilities of multiple events. That is, that you do something 2, 3, 4 times. So an example of that. Well, what's the probability you take a deck of cards and you turn over 2 cards and they're both aces? That would be an example of this situation. What's the probability that it rains 3 days in a row? What's the probability that a woman who has 3 children gets nothing but boys? So, right, 3 things are happening, 3 children, 2 cards are being played, 2 things. You know, raining, whatever I said, 4 days in a row, that would be 4 things. One way in which we can do these types of probabilities is called a probability tree, right? It's a tree diagram. We're going to show you how to calculate that. But before we look at that, we need to be aware of 2 possible situations. There is with and without replacement. So I'm going to show you an example of a tree diagram in both situations. This is with replacement. We'll do that first. So suppose that we have a deck of cards. And I want to know the probability that you get 2 cards and they're both hearts. But because it's with replacement, this is how the story will work, right? You've got a shuffle of your cards and you take a card out and you put it on the table and it's red or it's hearts or it's clubs. Once you've written down what it was, that card gets put up and it gets replaced back into the deck. That's what with replacement looks like. So what that says is that each time you do whatever the event is, in this case, you're going to do it twice, but each time you do it, the probabilities don't change. So that's the key feature about with replacement. The probabilities don't change. How do you draw, or how do you use this thing called the tree diagram? Well, you start with a little dot, and there are 4 things that could happen on the first card. You could, for instance, have a club, a diamonds, a heart, or a spade, right? Now, what's the probability that the first card is a club? Well, the answer is 1/4. Actually, it's 1/4 for all of them. So far, so good. Now, second card. Well, the club could be those 4. The diamonds could be those 4. The hearts could be those 4. And finally, the spades could be those 4. Now, for each one of those, it could be a club, a diamonds, a heart, or a spade. And you kind of see that these tree diagrams get ugly really quickly. Now, since I'm only interested in the probability that both of them are hearts, right? Both are hearts, then I would be going, first one is a heart, and wouldn't the second one, the chances that it is a heart is still 1/4. So the probability that you get a heart and then another heart is simply just the probability of a heart times the probability of a heart. In this case, it's 1/4 times 1/4. So you can have your probability. It's 1/16. Now I've got most of that tree diagram done, even if I haven't told you each of these. Would you agree each of these tiny little branches are always going to be 1/4 a chance, right? They're all equally the same. So what's the probability that you get a heart or a club? Or I should say, and a club. Well, a heart and a club could happen that way. But couldn't you get a heart or and a club in that order? Couldn't the first card be the heart and the second one would be a club? And that's going to happen with a probability of 1/4 times 1/4, which is a 16th. And if you switch places on it, isn't the other one also 1/16? So what's the probability that in any order you like, you get a heart and a club? What do you think I do with these 2 probabilities I've just found? I know that getting a heart first and then a club second has this probability, basically using that calculation. And a club first and then a heart second, which is considered a different event, is that. What do you think we do to both of those to come up with this one? You think I should add them, multiply them, subtract them, turn them upside down? What should I do with them?
Then multiply?
Oh, like one thing followed by another? No, but I like the thinking. You're trying. Okay, here goes. You add them together, in which case you get an 8. Do a smaller one. Suppose we only work on cards being red or cards being black. So when you do the first card, The probability that it's a red card is half the time. The probability it's a black card is half the time. And then you pick the card up, oh, it's red or whatever it is, you put it back in the deck, you shuffle them again, and you take a second card. So it's red and black, red and black. Since you put that card back in, the probability that the second card is red is still a half. In fact, all of these are still a half. First card is red, second card is red. The chances that you get red and red is 1/4 time, is 1/2 times 1/2, which is a quarter. This is the red one first and a black one second. And that's also going to be 1/4. And then a black and then a red is 1/4. And lastly, a black and then another black. Now, this tree diagram I can use to answer quite a few probability questions. For instance, what's the probability that I get 2 black cards? Well, if you look through the combinations, there's the 2 cards being black. The answer is a quarter. Suppose I asked you, what's the probability after I've drawn 2 cards, replacing it each time, that I get 1 of each color? Look at these guys up here. What combinations represent 1 of each color? One of each color. Which one?
Red and black.
Correct. Wasn't hard. And what's the other one?
Black and red.
And the probability of red and black is a quarter. And the probability of black and red is also a quarter. So the answer is a half. Okay, I think we need to do another one of these. Okay. Let's imagine that we're in a country where the probability that you have a boy is 0.6 and the probability that you have a girl is 0.4. Or at least that's the probability that they live. China had a one-child policy for quite a long time. I don't know if it's still going. It might be in the countryside at least. And essentially, you're only allowed to have 1 child. They were trying to reduce the population. And boys, I know it's sexist, but if you only have 1 child, you wanted a boy because the boy was going to be the person who would look after you when you got older. And that's how their culture would work. A girl, however, if you got a girl, she'd get married probably to someone, and that she would join their household, in which case you were in trouble. So it did increase abortions of girls. So that isn't that unrealistic. So let's imagine this other country. So it's not China, it's just another country, and this is the probability. And I want to find the probability that I get, in a family of 3, I get 3 boys. So if you went and found in this country a family exactly 3 children, what's the probability that that family would have 3 boys in a row? You know, if you go boy and girl, that's the first child. Well, a boy is 0.6 and a girl is 0.4. Now, since we're making the assumption that the probabilities never change, we would call this a with replacement. I know you're not replacing children, that, you know, it means the probabilities don't change. So if you were looking at the second child, wouldn't it still be a 0.6, 0.4, 0.6, 0.4 spread? And then you'd build it one more time. The third child could be a boy and a girl. These are quite long tables, so you never really want to do more than 3 because they just become too clunky and very impractical. So 0.6, 0.4, it's the third child. 0.6, 0.4, 0.6, 0.4. And we are going to set up a table. And on this table, we're going to put the number of boys in the family and the probability of that happening, right? So you may have no boys in the family. That's because all 3 of them were girls. You might get 1 boy in the family, you might get 2, and finally you might get all 3 are boys. And then at the end, I'll put a total. Okay. At these places here, the tails of the probability, I'm going to put the probability of that particular combination happening. And simply what you do is you just multiply the rows together. So what do I mean by the rows? I mean, you multiply 0.6, 0.6, and 0.6 in this case. Okay, what's she doing now? Come on, Chloe, out of there. You should know better. So if you do 0.6 times 0.6 times 0.6, you will get 0.216. I'll do it in green. If you do this one here, won't that be a boy, and then a girl? So that's going to be 0.6 times 0.6 and finishing with a 0.4. And that's going to be 0.144. If you go boy, girl, boy, you also get 0.144. If you do boy, girl, girl, that's going to be a boy first times 0.4 for a girl and another 0.4 for the next girl. And that ends up being 0.096. And if you do this one, you get girl, boy, boy. So that ends up being 0.4 times 0.6 times 0.6. That's back to 0.144 again. And this one is a girl, a boy, and a girl. 0.096. This is a girl, girl, boy. I believe this is also 0.096. And finally, you got all the girls. 0.4 times 0.4 times 0.4. And that ends up being 0.064. Do a quick check, I did them right. That one's good. 2 boys and a girl. 2 boys and a girl. Boy and 2 girls. Girl and 2 boys. 2 girls and a boy. 2 girls and a boy. All the girls, right? Probability you get no girls is that no boys is this one. So this is 0.064. So that one's kind of done, so I don't need to use that again. There is more than one way, isn't there, that you get a family with 1 boy in it. Right? It's going to count 2 girls and 1 boy, but doesn't it depend if the boy was first, second, or third in the family? So as you go through these destinations, these ends of the tree, you're looking for a combination of one boy with two girls. So if I do one boy, let's do it here, and two girls, I get that one. Is there any other places where that happens? So I've done, the one I've done, a little asterisk, is a boy, girl, girl, right? Boy, girl, girl. Where is the other combinations where you get a single boy in the family?
There's like two more.
There is.
It's like second to the bottom and then third to the bottom.
Okay, so girl, girl, boy. And finally, girl, boy, girl. Have you noticed that every single one of those three ways ends up being the same probability of happening? And so if you add those together, and the easiest way to add them is just to go 0.096 times 3, you get 0.288. Now, if you go to the, I'm running short of colours here, if you go to the next situation, there are going to be two boys and a girl now, right? And two boys and a girl happen here, and happen here. Do you notice that those are also the same number, 0.144? Right. So you could have two boys and the last one was a girl, the first one was a girl, then you had two boys, but no matter how you do it, the 0.144, and there's three ways that that happens. And I'm looking at 0.432. And then all the boys happens at the end. What should this total add up to if everything that was done here was multiplied and added, correct?
1.
Okay, so fingers crossed. 0.064, that's the chances you get no boys. Add 0.288, add 0.432, add 0.216. Am I good or am I good? I'm on a roll today. It's 1. From this trio diagram, and this is basically a summary of the information that's on that trio diagram, you can answer any kind of question about a family of 3 children in this country. So if I went and said to you, what's the probability that they were all boys? You would simply say 0.216 or 21.6%. Isn't that quite a high percentage? What's the chances in this country that they were all girls? Well, 0.064 or 6.4%. Isn't that more than 3 times more likely to happen than this one? Now, if you're interested in you're looking into, one-child policy in China, it's not that every family had one child, although in some horrible cases, they would just force them to be aborted after the first child. Especially in the countryside, the people just had more children. But one of the rules that they had was only the first child could be educated. So the state would not pay for the education. Only one child could go to university. Only one child could get a government job, right? It's basically they control your life by bureaucracy, which is a good reason why you should never let countries tell you what to do, governments at least, because governments have a problem with power and they like it too much. Not that I've experienced that today in America. Nobody's ever told me what I should or shouldn't do. I'll let that one slide. So here we go. Now I could ask, you could figure out any question you like. Couldn't you say, what's the chances that you found a family where the first was a boy, the second was a boy, and the third one was a girl? Wouldn't that be this one up here? So you have to be able to create this table, but once you've created it, and it's a pain in the butt because they're very big, can't you create one of these as a summary? Or you could just use this table and add them up as needed. Let's do this weird one. What's the probability that the last child was a boy? and it's kind of a trick question. What's the probability that the last child was a boy? I said it's a trick question, but there are two ways to do it. There's a dead easy way to do it, and then there is use a tree diagram. Right? The dead easy way to do it is, isn't it still 0.6 no matter which one of the children it is? Right? A boy is 0.6 whether he's the last one in the family, the second one in the family, or the first. But if I used this table, wouldn't the probability of getting a last one being a boy would be that situation there, because that's a boy. It would be that one. It would be that one. And lastly, it would be that one. What do you think you would get if you added all of those 4 dots together? You would get 0.6. Check it out if you like. Are we feeling a little bit more comfortable about how to create these probability trees and how they can be used to answer questions like this? Because if you didn't have this tree, and I went and said to you, right, chance a girl is 0.4, the probability of a boy is 0.6. What's the probability that you get 2 boys and a girl in any order? Aren't you going to have a problem just trying to create that if you didn't have this table or that? So there's no way of essentially avoiding that. Do you want to see another one of without replacement? Because these are big questions. Some of you are nodding, some of you are not so sure. Okay, let's do a little vote thing. Do you know those little icons that you have on the right-hand side called reactions? I'm going to put a surprise face up. There I am. What I'd like you to do is, if you want to see one more, stick a thumbs up. And if you don't want to see one more, just leave it blank. Is that the best way to do it? Yeah, okay. So go for it. How many?
What was it again?
If you want to see another example of this tree diagram process, thumbs up. Actually, I probably don't need any more because I got enough of you there. I think it's worth it. So this will be kind of hopeful, well, not hopeful, but this should be our last time for this one without replacement. So a without replacement situation is essentially any situation where the probabilities do not change, right? So the probability that it rains in July is 0.3. And so the probability that it doesn't rain, which I'm going to call dry, is 0.7. So we're going to be looking at a weekend in July. And so 2 days in July, and we're wanting to find out what the probability of, both days being rainy or whatever. So I'll start off with my tree diagram. I'm only doing a 2-1 of this time. So you could have rain or it could be dry. And then the second day, it could be rain or it could be dry. Could be rain, could be dry. And in this case, 0.3 that it rains, 0.7 that it dries. 0.3 that it rains, 0.7 that it dries. Are you comfortable with, that's the first day, and this is the second day. Are you comfortable with the construction of the tree and the numbers that go in it? Now, I'm not doing it, but couldn't I do a third day and it would be just that horrible big? But you get the gist of it with 2 days. So that's what I'm doing. So on these ones then, the ends, that's these guys here. This is rain and then rain, which if you multiply them together, gives you 0.09. And a rain and a gives you 0.21, and a dry then a rain gives you 0.21, and finally a dry and a dry gets you 0.49. As a quick check, shouldn't all these four add up to 1? Shouldn't these four all add up to 1? And they do. Now, I'm going to create a different kind of table this time, just to show you can do it in different ways. This is going to be the first day. And the first day, it could rain or it could be dry. And over here is going to be the second day. And on the second day, it could rain or it could be dry. So there are 4 boxes here. Let's see how this could be used to create a categorical table. Right. The one my finger is pointing at is both the first and the second day being rain. So that ends up being 0.09. If the first day is dry and the second day it's rain, the first day it's dry, second day it's rain, that's 0.21. This box here, the first day is rain, the second day is dry, first day is rain, second day is dry, is 0.21. And this box is dry and dry, which is 0.49. So I've taken the information that's here and I've made a little contingency table, right? So called a categorical table. And I could ask questions like, what's the probability that both days it rains? Okay, what's the probability that in both days it rains?
.09.
Okay, so it would be where my finger is, or you could get it from here, right? Which is, there are 9% chance that it rains, right? So you turn, you're going to, you know, well, we all live here, but you're going to go over to Seattle this coming weekend. The chances that you're just unlucky and it rains both days is 9% of the time. If you're a gambling person, it's not too big a chance. I could probably make it. But you can also do these probabilities. What's the probability that it doesn't rain on any day?
It's 49%, isn't it?
Because isn't that just a hidden way of saying it's dry on both days? And I could ask a question like this. What's the probability that it's dry on the first day, given that it rained on the second day? Right, we call these events conditional probabilities. So if I tell you that it's rained on the second day, right, doesn't that make the world just those two numbers? And so I know that's a decimal, but think of it as 9% and 21 if you need whole numbers. So the bottom number is just these two added up, which is 0.3. Right, so the world only consists of them. Now, which one of these is dry on the first day? It's what, 0.21? And if you take the 0.21, the dry, out of the total for that row, which is 0.3, whoa. Does that surprise you? That it's a 70% chance that it's dry on the first day? Because isn't that just the normal probability that it's dry on any day? And that is without, sorry, that is with replacement. So we're now going to see the other situation. We're going to do probabilities without replacement. And the key feature about these is that probabilities change. Have you noticed in the tree diagram, it's 0.7, it's 0.7 every time, right? Whether it's the first day, the second day, or the third day, if the child has got a 0.6 chance of being a boy, the next child has still got a 0.6 chance of being a boy. Now we're going to look at probabilities of without replacement. So I'm going to do my cards again, right? So you have 52 cards. And we're going to look at the probability that you get 2 aces. But in a real game of cards, don't you shuffle the cards, you turn the first one over and it goes in the deck, right? But don't you now only have 51 cards left because the first card is down. And so can you see that the probability of getting the next ace is going to be different than the first time because there's less cards and less aces, right? So that's the trick. So I'm going to have a little probability tree that's made up of only 2 branches. You try and make these trees, you know, as simple as you can. So this is going to be the first card. And it's going to be an ace. And the other one, I'm just going to call it not an ace. Now, in a normal deck of cards, isn't the probability that you get an ace is 4 out of 52? What is the probability that you don't get an ace?
48 out of 52.
The other 48, exactly. Now, second card could be an ace, but it also might be that it's not an ace. The second card come from here, could be an ace, and over here, it's not an ace. But the probabilities will change. It won't be 4 out of 52 and 48 out of 52. That's what it would be like if once you took the first card out, you looked at it, it's an ace or it's not an ace, whatever it happened to be, and you put it back in the deck, you shuffle them again, then you do the next card. When you talk about this ace here, you're coming from here. That means the first card was an ace. That has 2 effects. Doesn't that mean there's only 51 cards? How many of those cards are aces? Because that's the probability of this happening.
3 out of 51.
Now, 3 out of 51 are aces. Won't not aces be the rest? That's the easy way to do them. So there's still 51 cards, right, in the rest. 3 are aces, so I believe the other 48 are not aces. You happy with that, Kevin? Now, if you go down here, the first card was not an ace. What's the chance that the second one is? Well, there are 51 cards again, right? But you know the first one was not an ace. Now, doesn't that mean you've got 4 out of 51 chance of getting an ace in that situation? And the not ace followed by another card that's not an ace. Well, there's 51 cards. Since this one is not an ace, don't you basically say whatever's left? And what is left when you take that away, I believe you get 47. So back to my probability of getting 2 aces. If you multiply the paths together, that's the probability of that particular combination of events. So I'm going to take 4 52s, that's the first one, and multiply it by 3 51s, which is the second one. Are you comfortable about that? Where that came from? So you grab calculators, you go, oh, you probably don't need brackets, but you know, I always figure out it's just safer to put them in. Because sometimes the order of operation gets a bit wonky. Now I hit that, and I'm going to have to round these answers off because they're really ugly decimals. So 0.004 5 to 3 decimal places, which is 0.5%. But 0.5%, what's that? 1 in 200, how about that? So if you take a deck of cards and you shuffle them and you turn over 2 cards, right, boom, boom, like blackjack, the chances that you get 2 aces, isn't it tiny? A 1 in a 200, 0.5%. What's the probability that you don't get any aces? So out of these 4 guys, which one would be, you did it twice, boom, boom, and you didn't get any aces at all? Which one of these, there are only 3 left, which one of these would be that situation?
Bottom one.
Yeah, the bottom one, correct. So it's 48, don't know why I've went green here, 52. 47 out of 51. It's going to be pretty ugly, but here goes. 48 divided by 52 times 47 divided by 51. And as a decimal, that's 0.851, which is about 85.1%. Can you see that there's a great chance that you're probably not going to get any aces, right? 85% of the time, you're not even going to get 1 ace. Now, for completeness sake, what's the probability you get exactly 1 ace? If you get exactly 1 ace, isn't that the situation? You got an ace and then the other one wasn't? Or the first one wasn't an ace and then the second one was? So these 2 guys here that I'm now going to put little red dots on, wouldn't these 2 be that situation? So you find the probability of each of these and then you add them up. Well, if you go this way, you get 4 out of 52 times 48 out of 51. And if you go the other way, you get 48 out of 52 times 4 out of 51. Since we're running short of time, let me tell you that is 85.6%. So 85.6, that's 14.4%. So if you play blackjack and they deal you 2 cards, aren't you probably going to get an ace, 1 ace, exactly 1 ace, about 14% of the time? Aren't you going to get 2 aces about 0.5% of the time? And isn't the vast majority of the time you're not going to get any aces at all? Now, can you see how that might be helpful for a gambler to know?